We're looking at a road cutting in the French Alps. It's limestone caught up in a major thrust zone, and it's riddled with white veins. These represent fractures. The fracturing created voids into which new mineral precipitated. The mineral here is calcite, the same material that makes the surrounding rock. It's not unusual. Veins are often made largely from their surroundings. But despite these local origins, they are recording important geological processes. There are two parts to this. For calcite to precipitate, it must first have dissolved, which in the earth is commonly termed pressure solution. And then it has reprecipitated in the veins. Collectively, these processes form a deformation mechanism that structural geologists call diffusional mass transfer, or DMT for short. And we'll look here at how DMT is represented in deformed rocks and how we can use some of its features to chart the deformation. Well, let's start off with veins. Veins are filled fractures. They're a precipitation site for new minerals, and on these photomicrographs, the veins are lying in fractures, and the fill is represented by this sparry calcite, significantly coarser grained than the host rocks surrounding the veins. So this is an example of a precipitation site, a cavity in the rock. So it's quite easy to recognise where new material has been precipitated. Rather harder is to consider where it came from, because we're going to be looking for material that's gone. So consider the graphic on the right, which shows two grains abutting each other, being loaded vertically, so a maximum compressive stress acting vertically and enhanced on the grain boundary. The stress will enhance the solubility of rocks. And the more soluble of the two grains is more likely to dissolve than the less soluble. So if we allow the deformation to progress, the less soluble grain will appear to eat into the more soluble, leaving a grain with a bite taken out of it, or strictly dissolved out of it. So let's look at the conglomerate on the photograph. You can see that the main grain here appears to have thumbprints in it, which are indentations within which less soluble grains once sat. It's an example of a pitted pebble, and it indicates that there's been dissolution, in this case of the pitted pebble itself. So let's explore how this mechanism might work to accommodate deformation in rocks. Let's consider this grain here, and it's being loaded with a horizontal maximum compressive stress, and consequently the grain boundaries onto which that stress is acting will tend to dissolve. In this particular case, we'll imagine that the material doesn't go very far. It'll diffuse to another part of the grain boundary, away from the area acted upon by the maximum compressive stress, and it will reprecipitate there, like this. So along the grain boundaries represented by the red lines, we dissolved material away, and we reprecipitated that material in fringes top and bottom of the grain. As a consequence, the grain has acquired a new shape from originally circular to now elongate up and down the screen. So we're building a shape fabric through the dissolution and reprecipitation processes. This is why diffusional mass transfer is an important deformation mechanism. So what might be the controls on it beyond the stress? So we can explore this question using a household analogy, which is a cup of coffee and some sugar. You'll know that sugar dissolves more easily in coffee if that coffee is warm. So solution processes are temperature sensitive. But you also know that they're grain size sensitive. A sugar lump will dissolve more slowly than caster sugar in the coffee. So finer grain rocks will deform more easily than coarser grain rocks. We can explore this now. So here we've got two grains represented by the blue circles, and again we'll have the maximum compressive stress acting horizontally. So let's say that over the duration of the strain that you can dissolve a small amount of grain length, and this length is common to both grains. Let's allow the deformation to progress. So let's say we've dissolved away 0.5 millimeter of grain. We have the same length, therefore, of dissolution, and we've precipitated the same amount of fringe, top and bottom, of the grains. But these are proportionally different, because our 0.5 millimeter of solution represents a greater proportion of the smaller grain than it does for the larger grain. So this illustrates part of the grain size sensitivity of this process. And we can capture this by looking at the elliptical shape of the grains. The smaller grain has got a greater ellipticity, therefore a higher strain, than the larger grain. So finer grain rocks deform more easily. Now let's consider a rock made of different grain sizes. We have an aggregate of small grains with one large grain in the middle, part way through the deformation. And now let's represent these by their strain ellipses. So the finer grain material has got a fairly pronounced ellipticity running up and down the screen. The larger grain has also got an ellipticity in that orientation, but is not as marked, so the grain is not as deformed. In other words, the strain in this rock is heterogeneous. If there's an abrupt strain gradient, as there would be if there's one large grain surrounded by small ones, then the strain is also incompatible, meaning that a void is likely to open up in these areas of incompatibility. The void is a dilational structure, so it'll open at the top and bottom of this grain, and into that cavity can be precipitated new mineralization. These features are called pressure shadows. They're characterized by the fibrous growth of the pressure shadow fill. The reason for that is that the cavity will open gradually and the fibers will chart that gradual opening. So the matrix deforms, the cavity opens on the extensional or dilational side of our more rigid grain, and we get that type of structure. And we can see an example in nature in this rock from the French Alps. The beige material is essentially a dolomitic sand, and a large clast of it is marked here with X, surrounded by finer grain material. The white comet-like fringes around here are pressure shadows into which has deposited fibrous gypsum. So the fibers are growing along the axis of the pressure shadow, charting its incremental opening in this direction. So pressure shadows like this and the fibers they contain can tell important stories about the incremental kinematics of deformation. We can see another example here, also from the Alps, but this time we have a large sandstone clast sitting on dark grey limestone that has been pulled apart, and we can see filling the fractures and even between some of the grains in the sandstone is a fibrous growth of white mineral, which is calcite. So those fibers are charting the incremental stretching, rather like pulling out a piece of chewing gum, of the pebble of sandstone, like this. Another important place for reprecipitation of synkinematic mineralization is on a fault plane. These structures are called shear fibers, and we can quickly show how they form in the block diagram on the right, which shows a fault plane with a hanging wall in pink, and the fault plane has a step on it. And we'll move the hanging wall off to the right, which will create a void on the step, and the void becomes filled with fibrous new growth of a mineral. As the void opens, the minerals grow greater in length, revealing, when we strip off the hanging wall, a fibrous growth represented by those blocks of black and white. So the fibers are growing in the direction of fault slip, a really useful kinematic indicator. If we look at the fibers in detail in here, we can look at these in a photomicrograph to show how the fibers grow incrementally. So here's a photomicrograph looking side on to one of these fibers. The fibre itself is along the top of the photomicrograph, and the lower part of the image shows a sparry calcite, which represents part of the wall rocks to this fault zone. So the fibre has this strange barcode look of black and white stripes. And these stripes are rather like tree rings that have charted the incremental growth of the fibre. The fibre's grown off in this direction and pulled itself apart a little bit, into which new calcite is precipitated. So the fibre has cracked open and then sealed itself up by more calcite precipitation. The deformation mechanism is called crack seal, and it charts not only the incremental growth of the fibre, but also the small stick-slip behaviour of the fault plane. Each of these crack events is very much less than a millimetre in length, representing very small stick-slip events on our fault plane. Okay, so we've dealt a bit there with the precipitation sites. Let's go back to the dissolution issue. And a really common feature indicative of dissolution in rocks are stylolites, and they're common constituents in limestones where they enhance bedding planes. That's the situation we see here, where the stylolites form those highly irregular tooth-like features running horizontally across the image. So how do these form, and why are they so irregular? Well, let's go back to our cartoon showing the loading of two grains at their mutual grain contact. With this loading condition, one or other of these grains will dissolve preferentially. The one that dissolves is the one that is more soluble, and in any rock, even a homogeneous one, there'll always be one grain that is more soluble than another when asked the question across its common grain boundary. So the more soluble one gets eaten away. And there's a positive feedback mechanism in here as this situation develops. This means that this eating process amplifies. Let's explore this on this diagram here, where the red line represents a bedding plane. Often bedding planes will have little bits of impurity on there which will enhance this process even more. And across the bedding plane we have pairs of grains that are asking each other which is the more soluble. So let's allow this rock to compact. So in other words, we'll put more rocks on top that impose a vertical load that will ask the dissolution question across that bedding plane. So we generate an irregular bedding surface as different grains along that bedding plane dissolve. Initially this might be quite a random form, but the positive feedback mechanism will enhance it. Increasing the amplitude of our stylolites through time, the more rock we dissolve away. So high amplitude stylolites imply a lot of vertical dissolution, a lot of compaction in other words. And this process happens during burial, doesn't require any tectonics. Let's go back to a situation where the deformation is related to tectonics. Shortly we'll look at some deformed conglomerate, so let's set this up again in cartoon form. What we have here is a rock made of different class types, some more soluble than others, as labelled there. So the blue class are less soluble, the green class are more soluble. And we'll load it with sigma 1, the maximum compressive stress, vertical, and the minimum compressive stress, horizontal. So in other words, that square is trying to become a rectangle as oriented in the sketch. So let's impose some deformation. After deformation, the grain boundaries that are horizontal will have seen the maximum compressive stress, so those are the ones that have indented. The grain boundaries that are vertical face onto the sigma 3 direction, so those are the sites where the fringes of newly precipitated material will occur. In addition, the grains may crack open, in which case veins will open in a direction perpendicular to sigma 3, filled with precipitate. Let's see if we can recognise these features in a deformed conglomerate. So here is a conglomerate from the French Alps. The big blocks in here are limestone, and there's a small proportion of quartz sand in here as well, but we're not really worried about that. It's the large limestone on limestone contacts we're interested in. Let's pick out some grain boundaries of this one here. Look at its shape. That wasn't the depositional shape of that clast. is being eaten into by the other grains. So we can infer that they have a dissolving clast in the middle and two indenting clasts either side, which presumably therefore were marginally less soluble than the clast that has been dissolved partially away. Now in this rock there are no fringes on the conglomerate clasts, rather the dissolved material is at least partly reprecipitated in a series of veins which are running up and down the photograph. So we can imply this loading condition from the structures in the rock. So we can use these structures to infer the loading condition experienced by the rock while it was deforming. As we saw earlier, dissolution processes are particularly pronounced in fine-grained rocks. So here is a fine-grained siltstone with fine sand, and there's a vertical foliation and horizontal quartz veins. The quartz veins themselves are partly dissolved away, so they've got small breaks and offsets on them as arrowed. This pressure solution cleavage is commonly spaced and can be quite common in fine-grained rocks, even siliciclastic ones like this. But in fine-grained carbonates it can be particularly prominent. So that's a quick tour through the diffusional mass transport deformation mechanism involving the dissolution of material and its reprecipitation either on local grain boundaries or in veins. Collectively, these processes can be sometimes termed pressure solution, although strictly that's only referring to half of this process pair. Diffusional mass transfer, DMT, is an important player in the deformation of rocks, especially in the upper crust. We've seen that the texture of veins and pressure shadows give unparalleled information on small-scale strain histories, the stretching that opens those cavities, because these structures can be filled by fibrous growth. We've only seen a few examples here, but veins can also be economically important, hosting valuable mineral deposits. Placing veins in their tectonic context can make the difference for successful resource exploitation.